Okay, so for your first example here, the half-life is given as 1620. How long will it take for 60 grams to hit 5 grams? So this is the equation we should start with. 5 equals 60, half-life to the time over 1620. And this is what we need to solve. So I'll get, let's see, 1 over 12 equals 1/2 to the time over 1620. And got to rewrite it as a log. So this is the log in base 1/2 of 1/12 equals time over 1620. So time equals 1620 times the log of 1/12 over the log of 1/2. So it's only going to take 5,807, well, a fair amount of time. Okay. So the next question says it's estimated that 20% of a radioactive substance decays in 30 hours. What's the half-life? So the tricky part here is for the half-life question, 20% decays. How much is left? Because we're measuring the amount that remains, right? These formulas tell us how much remains at a given time. So it's actually 80%, and I started with 100. So that's one way that you could set this up. And it says that 30 hours have gone by, and I'm looking for that growth period. I'm looking for how long the half-life is. Okay, so we can rearrange these. You could also write it as, 0.8 as in 80%, and 30 divided by the period. So we got log base 1/2 of 0.8 equals 30 over p. So the half-life equals 30 divided by log 0.8 over log 1/2. Again, the change of base rule is what I'm using there. So 30 divided by log 0.8 divided by log 0.5. So at 93 hours. 93.189. Okay. So can I move that down now? Okay, no complaints. There we go. Okay, so the last thing that we look at for growth and decay is what if we want to take it at any given instant rather than having to do this at any point, like semi-annually or quarterly. So for example, in the real world, maybe you've bought a house which you pay monthly for your mortgage, or most people pay monthly, but then you go and win the lotto. Yay! But now you owe the bank money, right? You don't need to wait until the end of the month to pay the bank off your mortgage. You don't even need to wait till the end of the mortgage, right? You could go into the bank today and pay them back everything you owe, but the bank needs to be able to figure out, well, according to where we're at exactly on this day, how much money are you owing us, right? So instead of working with given periods, we'd like to know if we continuously grow something, what would the formula look like? So I'm going to need your help here because it takes a little bit of calculating. So let's see here. Roger, you're going to be quarterly. Ellis, you're going to be weekly. Let's see here. Stephen, you're going to be every hour. I'll tell you what you need to do with it in a second. Andy, you get to be monthly. Eamon, you can do daily. And then every second, Connor. All right. I guess I missed something. So you're going to use the formula as though you put $1 in the bank and it's being compounded. Quarterly would mean there's a 4. So for example, if I wanted to do daily, it would be 1 plus the $1. There'd be 365 to the 365. So what I want... Don't worry about that being that specific. 365 is enough for our purposes. But I'd just like to know what numbers you get. So go ahead and punch those in your calculators, and then we'll record them up on the board. Let's recap here. Roger, do you have a quarterly? 2.44. Now I totally forgotten all the people. Ellis, I think Ellis, you had one. Steven, do you have yours? 2.718. Can you give me a couple more decimals? 1, 2, 6, 6, 6, 3. Sure. Okay. Let's see here. Eamon, you had one, right?
2.714.
Is it daily?
Yep.
2.714.
5674. 85.
Okay. How about, let's see here. Monthly. Who is monthly? Andy?
2.61
301
303
303 29. You have to bear with me, I'm slow. Connor?
2.718 281,701.
And Ellis, what was your?
Mine is something like 1.77 times.
Well, probably one in the calculator. It probably needs to be, let's see here. Weekly is every 52 weeks, so 1 plus 1 divided by 52 to the 52. So I get 2.69.
Yeah, 2.69.
2596, blah, blah, blah. Okay, so one thing that's kind of surprising is, like, look at every second. That's a massive, massive exponent, like a huge number. How many seconds are in a year? And even though the exponents are getting bigger, because that fraction's getting smaller, it's actually not getting unrestricted growth. Like, it's not just jumping into an enormous number. So without studying some calculus, which you guys will have great fun with next year, these numbers are what we call this they approach a limit, which means if we went all the way to infinity, we'd actually get a value from this. And that's what we want, is if we did it continuously, that would mean there'd be an infinite number of payments made in a year. And the number we would end up getting is actually Euler's number, which is on your calculators. So if you want to pull up Euler's number, my calculator doesn't give me quite 718281828. Whoops, that's terrible. Let me do that again. 828. So you can see that when we get into seconds, it has Euler's number. It's 6 decimal places. So that keeps approaching Euler's number the bigger it gets. So that's kind of the best. As we increase the payment period, the size and the number of payments, we start to approach this Euler's constant. That's the best kind of, here's how it works sort of explanation I can give you without calculus. So here's the way it works with continuous growth and decay. It's almost the same, except the growth constant is Euler's number to its continuous growth. If it's a decay, what that means is you end up with a negative number for k. So you'd have a negative k in there. Okay, so just to show you how it works, if you had 25 million and the population grows continuously at a rate of 3%, then that means the population after 20 years is going to be 25 million e to the 0.03 times 20 years. So continuous growth is often more practical because it's not like we just say, okay, everybody ready? Have your babies now. Stop. Everybody wait. Everybody wait. Okay, it is now time again. Have your babies go. Right? There's a lot of things that I didn't say make your babies. I said have your babies. There's nothing to giggle about there. Anyways, so continuous modeling is usually more accurate for a lot of purposes because we don't want to just think of things happening in discrete time intervals like I guess notes on a chart every 4 beats sort of thing. So see if you can work that in your calculator. We'll find out what that number is.